It began like something from a routine shift at night. A dim light in a wide field survey, an addition made to an otherwise familiar star map. Initially, it appeared to be just another transient, recorded, and then discarded a small visitor traveling a long, isolated path across space. However, immediately, the insignificant visitor stopped acting like anything we had previously observed. What astronomers initially recorded as a new incoming interstellar object would soon force the scientific community and the world to renegotiate what it means to be observed by the universe. As of July 1st, a team looking at the sky in 2025 detected an object traversing the inner solar system. It received the clinically dry designation, 3I/Atlas, the third recognized interstellar interloper in modern history through observation. But that label concealed the way it would come to alter expectations. Initially, the object appeared familiar, small and bright, with a coma that suggested instability, and a tail that looked like it was exhaling like any comet from the visitor class. However, as telescopes trained on it, and as instruments that have long been the backbone of planetary science evaluated its actions, things didn't add up. A comet's tail should flow out of the sun's reach. The sun's radiation applies pressure to small particles, driving dust and gas outward in a recognizable pattern. The tail normally points away, trailing the nucleus like a streamer behind a swimmer. Atlas displayed an exact violation of that rule. Its plume pointed sunward, not away. Frame after frame, from different independent instruments and observatories across all continents, demonstrated the same narrow and persistent material jet aiming toward the sun. It was not a fan-shaped coma. This was a columnar, unrelenting arc directed at the star. At the same time, the image was confusing and tenacious. Observers began to whisper about perspective errors, data corruption, camera flaws, and artifacts. However, those initial explanations perished under scrutiny. Gemini South, the very large telescope in Chile, and images from space telescopes all confirmed the same ghostly phenomenon. The chemistry deepened the puzzle. Spectroscopy carried out by the majority of advanced instruments available revealed a chemical fingerprint distinct from normal comets. Water vapor, the common foundation of solar system comets, was not the dominant volatile. Instead, carbon dioxide ruled these objects. Atmosphere by a margin rarely if ever observed. CO2 abundances exceeded those of water by ratios many standard deviations outside what we consider normal. On top of that came a pronounced presence of atomic nickel and a nearly complete absence of iron vapor, an odd and unbalanced elemental palette that failed to map onto known cometary compositions. From a chemistry perspective, this implied a distinct nursery, a distinct set of formation conditions that freeze, trap, and eject components in unconventional ways. Beyond optics and chemistry was something even more important: dynamics. As analysts investigated positional data and fit ever more precise orbital solutions, they encountered minor but systematic residual differences between predicted and observed positions, differences that couldn't be reconciled solely by gravity. After the models were adjusted, a tiny amount of acceleration pointed sunward. Everything collapsed into place. The acceleration was small, somewhere around 4 times 10 to the negative 6 meters per second squared. However, over weeks and days, that small push accumulated into shifts of tens of thousands of miles. In modern spacecraft dynamics, this kind of acceleration sits on familiar ground. It is comparable to the gentle but persistent thrust produced by ion drives. What made it unnerving was the combination of thrust-like acceleration with a plume that behaved like directed exhaust. Narrow, steady, and coherent, not the turbulent and messy stream of dust we anticipate from melting ices. Scientists started making comparisons, both publicly and privately. If something wanted to slow down as it entered the inner system, firing a jet sunward near perihelion physically makes sense. You maximize the braking effect by shedding kinetic energy where speeds are highest. It's a trick our own spacecraft use. The data from Atlas proposed the same strategy. The plume's geometry, the relationship between the acceleration vector, and spectral evidence for ionized species, all implied behavior. That look designed, or, at the very least, a process that mimicked engineering so closely that natural mechanisms became difficult to match. This was not simply another curiosity. The orbit itself was shocking, a retrograde, excessively hyperbolic path slicing through the plane of the ecliptic in an alignment that brought it enticingly close to a number of planets in sequence. The likelihood of a random interstellar object threading a path that skirts Mars, passes Venus, and then passes Jupiter within such narrow windows was statistically disturbing. Calculations placed the coincidence at odds with expectations by orders of magnitude. It looked like a flight path, something planned to maximize the use of gravitational assists and planetary geometry. Gravity mechanics seemed to hint at purpose beyond mere chance. Then there was the timing. Atlas was scheduled to pass behind the Sun on October 30th, 2025. Solar conjunction is effectively a blindfold for astronomers.
The Sun's
glare and radio interference cut off direct observation and telemetry from Earth for a period that can last from days to weeks. Crucially, it is also the perfect environment in which a maneuver can go undetected. If an object wanted to change course without immediate detection, slipping behind the Sun would be the ideal moment to carry out a burn. The mere coincidence of a potential propulsion signature and an approaching conjunction was sufficient to trigger concern across nearly every major planetary defense and space analysis team. The James Webb Space Telescope and other high-end observatories turned their instruments toward the traveler. During spectrographic study, they found signatures that appeared more consistent with propulsion than random sublimation. The plume was composed of particles with a narrow range of velocities, a monoenergetic signature, similar to ionized exhaust streams. Xenon, the propellant commonly used in human ion thrusters, was not detected, but existing chemistry could still become ionized and accelerated under favorable conditions, resulting in a focused jet. The velocity dispersion and material distribution within the plume did not align with passive emergence. It appeared controlled, sustained, and tightly collimated. Given those details, a small group of researchers proposed a radical hypothesis. Atlas might possibly be a probe, not an overt alien spacecraft attempting contact, but an autonomous scout, the kind of device any advanced civilization might use. Perhaps a sensor platform designed to enter star systems, measure them, and alter course as necessary. If one imagines a network of such devices, a lattice of silent observers moving through the galaxy, then Atlas could be one node in a pattern humanity has only recently begun to notice. That idea intensified when analysts at JPL and other research centers began performing an unusual comparison. They examined Atlas's inbound vector and trajectory against those of the two previously categorized interstellar visitors, Oumuamua and 2I/Borisov. Each of those objects had already been puzzling in its own way. Oumuamua displayed mysterious non-gravitational acceleration and an unusual shape. Borisov possessed comet-like chemistry that nevertheless originated outside our solar system. But when layered together with Atlas, an alarming pattern appeared. Researchers found echoes in orbital geometry, mirrored vectors, recurring corridors, and alignments through the ecliptic that appeared less chaotic and more like a planned route. The technique, dubbed orbital fingerprinting, borrowed methods from satellite forensics. It searched for repeated motifs and correlations that might betray design or recurring behavior. When relativistic and observational corrections were applied and orbital arcs mirrored where necessary, the alignments became statistically difficult to explain through randomness alone. Some scientists began cautiously discussing the possibility of a recurring cadence probes launched or ejected in sequence, visiting systems according to a schedule too exact to dismiss as coincidence. That hypothesis, however, remains far from universally accepted. Science thrives on skepticism, and for every paper suggesting design, competing models attempted to contain the phenomenon within the framework of natural processes. One alternative explanation proposed that Atlas is not engineered, merely extreme. In this model, Atlas could be debris from a catastrophic event in another star system, perhaps a planetary collision or nearby supernova that hurled unusual material into interstellar space. Only the strangest volatiles might survive such conditions. The carbon dioxide-dominated chemistry could indicate formation in deeply frozen environments where CO2 condensed before water. The nickel abundance might suggest metallic parent bodies rather than primordial cometary composition. The sunward jet, in turn, could result from exotic sublimation physics under intense stellar irradiation processes, theoretically possible, but rarely observed because humanity lacks a large enough sample of interstellar objects formed under such circumstances. This explanation preserves naturalism, though at the cost of invoking structures and volatile behavior beyond anything currently catalogued. Then came the instrumental anomalies. During studies of the plume, several observatories reported temporary glitches, signal dropouts, and brief interruptions in data flow specifically, while pointing at Atlas. The anomalies were subtle but strangely consistent, confined to frequency windows commonly used for deep space telemetry and high-fidelity imaging. Some teams observed brief increases in background noise. Others detected temporary delays in data transfer, while a few reported false readings in spectrographs. These were not catastrophic failures. Instruments behaved normally while observing other targets. That pattern led to uncomfortable questions. Was Atlas interacting passively with our instruments, or were our systems being actively probed? If an object were designed to detect technology, sense instrumentation, and evaluate responses, then even tiny electromagnetic fingerprints might matter. Not as communication in the human sense, but as reconnaissance. Learning what frequencies we use, how quickly we react, and how we orient our telescopes. The glitches could have been diagnostic, rather than communicative, a way to map the sophistication of whatever civilization had noticed it. In that framework, Atlas becomes less an emissary and more an evaluator. The cosmic equivalent of a scientific instrument determining whether a planetary system is capable of detecting and understanding anomalies. Including in the public anxiety was the realization that Earth's detection capabilities are changing quickly. The ultimate Rubin Observatory was stepping up its game, and its combination of deep, wide, and fast survey capability. It promised to send the number of interstellar objects found escalating from one intruder per decade to many per year. Having more eyes, and AI-aided software that was smarter, presently combing terabytes of detection data each night, meant that things previous generations would have missed were now being measured, analyzed, and catalogued in actual time. That ought to be reason for celebration. Better models, more data, deeper comprehension of the galaxy's inventory. Atlas and similarly strange cases, it also meant that we may be witnessing the tip of an iceberg. Numerous insignificant anomalies, when joined together, reveal the fabric of movement across our solar system neighborhood. When you begin to connect the dots, the picture becomes harder to dismiss. Some scientists started developing hypotheses made up of multiple sightings from across the galaxy, a web of interconnections, paths that at first appeared haphazard, but eventually formed plausible routes running through the solar system, with geometric precision that could only be seen through a wide time scale and high-resolution datasets. Rather than isolated intrusions, these objects appeared as nodes in a larger structure, a galactic scaffold, a grid of observation points left by agents whose durations exceed human centuries. The implications, if true, are staggering. In a sense, we are not alone. We share a galaxy with other matter and energy, and perhaps we are being watched by things whose actions point to deliberate placement. Of course, this kind of claim calls for extraordinary scrutiny. Extraordinary claims demand extraordinary evidence. The research community reacted accordingly. Teams replicated analysis, requested independent data, and required open sharing of raw observations. Peer review and duplication, the bedrock of the scientific validation process, got underway. Directed simulations incorporating isotropic mass loss, thrust, and particle emission were examined on supercomputers for weeks. The outcomes were awkward. Only by allowing models to include deliberate emissions in the right direction did the data consistently match observations. When randomness was enforced as a strict assumption, the residuals remained. It is a harrowing moment when nature refuses to cooperate with the simplest and likeliest explanation, and the narrative inevitably spilled into the public realm. Newspaper headlines all over the world alternated between fear and wonder. Commentators discussed the likelihood of alien probes. Online forums were filled with speculation about reflective tarps over moons and communicating by radio with strangers in the sky. NASA and the European Space Agency remained cautious in official declarations, reiterating uncertainty and restraint. However, beneath careful bureaucratic language, a new kind of existential consideration started to creep into discussions between policymakers, ethicists, and even military analysts. If objects are intentionally surveying star systems, what are the protocols for interaction? Does observation necessitate a response? Should humanity try to alter the trajectory of an object from another galaxy?
Who decides?
Naturally, there is a lengthy and contentious history of scientific protocols concerning encounters with extraterrestrial intelligence. International procedures and first contact scenarios have been debated for decades, but Atlas was not a clear message in any way. It was not transmitting radio beacons or Morse code. It was a physical phenomenon that read like an inquiry without speaking. The discussion quickly divided into groups. Some supported restraint, avoid acting hastily, check for responses carefully, and ensure all decisions are global in scope. Others supported emergency planning. Get ready to communicate, observe, and, if necessary, defend. There were also practical concerns based on risk assessment. If an object can maneuver in ways we cannot monitor it during solar conjunctions, could it alter its course enough to endanger satellites or planets? The probabilities of direct impact remained negligible. The energy required to turn an interstellar flyby into a collision with Earth is enormous. Yet the mere possibility that an object could execute a burn unnoticed while hidden behind the sun raised concerns about strategic surprise and the solidity of planetary defenses. Agencies responded by improving blackout contingency protocols, utilizing radio data gathered from spacecraft throughout the solar system, and coordinating efforts to maintain observation during critical conjunction windows. The human element followed suit. Observational scientists and universities suddenly found themselves at the center of a cultural event. Email switched to encryption. Shared streams of data moved rapidly through institutions, and the once arcane practice of orbital reconstruction entered late-night public discussions. There was excitement too. Not only fear. Young researchers were thrilled at the possibility of contributing to discoveries that future generations might study, alongside the names of Christian Huygens and Nicolaus Copernicus. Older colleagues, hardened through years of subtle discoveries and false alarms, cautioned strict skepticism. The struggle between discipline and wonder, between hope and method, became part of the story itself. As October 30th drew near, Atlas slid into solar conjunction. Observers could only sit back and watch history disappear beneath the glare of the sun. Instruments switched to law-specific protocols. Teams prepared for telemetry gaps, while simulations modeled every possible post-conjunction scenario. The question was terrible in its simplicity. What would happen beneath the sun? It might be nothing at all, a pause, an optical illusion, or a natural process finally explained by a more comprehensive model. Or it might be something decisive, a reset, a maneuver, a brand new trajectory only visible once the object returned into view. When Atlas reappeared on the opposite side of the sun, the initial findings produced the kind of collective sigh rarely heard in science. Eyes scanned familiar arcs, instruments compiled spectral images, and algorithms compared new positions against earlier forecasts. The world waited for a sign. The same sunward plume, a change in velocity, any indication the object had used its period of concealment to maneuver. What emerged was both disappointing and revealing. Some parameters had changed slightly. The most telling shift was a subtle redirection consistent with a minor propulsion event. It was not dramatic enough to trigger immediate alarm, but it was significant enough to imply that choosing observation over intervention had consequences. Post-conjunction interpretations remained deeply divided. Some researchers pointed to the correction as evidence of autonomous transport. Others argued the shift remained within acceptable margins for models involving extreme sublimation. As science often does, the truth sat uncomfortably in uncertainty. There was no denying, however, that discussion and observation intensified. More interstellar objects were discovered in the months that followed. Some displayed strange signatures, others appeared perfectly ordinary. Among them, at least one candidate showed no coma at all, only a cold, dark core soaring inward from the depths between stars. For the first time, the sample size of interstellar visitors became large enough to support meaningful statistics. Patterns could be weighted, anomalies could be compared, emergent properties could begin to reveal themselves. Looking back, the episode forced a cultural recalibration. Humanity had built telescopes to look outward and spacecraft to leave home, but we had never truly prepared for the possibility of being observed at this scale. The galaxy, once imagined as a mostly silent expanse interrupted by occasional drifting rocks, suddenly appeared busier and perhaps intentional. Whether Atlas and its kin were artifacts of ancient technology, fragments from violent cosmic events, or something in between, the discoveries transformed the way we think about planetary defense, neighborhood awareness, and the ethics of interstellar inquiry. The significance reaches beyond physics alone. If intelligence can launch probes across the galaxy, and if those probes can time their appearances and adjust their sensors, intentionally, then humanity may have crossed an invisible threshold. Detection is no longer merely a technical accomplishment. It becomes a cultural turning point. Our observatories are not only tools for discovery, they may also act as signals responses we do not yet recognize. Humanity is now forced to ask difficult questions about secrecy, about how to respond to potential observers studying our digital signatures, and about the responsibilities of a species becoming visible to a wider, cosmic audience. Even if future evidence ultimately transforms Atlas into a purely natural class of extreme interstellar objects, the consequences would remain profound. Discovering a new category of bodies dominated by CO2 chemistry, high nickel content, highly directional sublimation would rewrite models of planetary formation and expand our understanding of galactic material diversity. That alone would inspire new searches, laboratory experiments, and new models for chemistry under conditions humanity has never reproduced. Often, nature surprises us with behaviors that appear engineered simply because our imagination has not yet caught up to the complexity of physical processes. The universe is stranger and larger than our metaphors. However, if the engineering hypothesis gains stronger support, if Atlas and similar objects are confirmed to be autonomous probes, then humanity faces an entirely different class of questions. What are their intentions, if any? Are they relics from civilizations long gone, components of a surveillance network, a galactic census, benign curiosity, or fragments of systems more complex than anything we currently understand? The answers would test the boundaries of both science and diplomacy. For now, the prudent path is continued observation, refining instruments, strengthening international cooperation, and creating protocols for carefully measured responses to future anomalies. In the years ahead, both trepidation and exhilaration will remain. Rubin and other survey telescopes will flood the scientific community with detections. Analytical systems will sift through them searching for irregularities. Collaborative networks will compare measurements across wavelengths and platforms. Meanwhile, scientists, policymakers, and ethicists will continue debating the social and observational consequences of existence on an interstellar scale. The emergence of one Atlas acted like a mirror, one that reflected not only the object itself, but humanity. It forced us to confront how we process surprise, how we absorb unsettling data, and how we balance curiosity against caution. It reminded us that technological advancement creates visibility, and visibility invites response. Whether Atlas is a crafted scout, a time capsule, or something beyond both categories, it pushed humanity into a new conversation about our place in the cosmic environment. The story is not over. As more eyes sweep across the heavens, more anomalies will emerge. Some will be ordinary, some will be strange, a few may be shocking. Every new discovery will challenge assumptions, biases, and protocols. Whether these visitors eventually reveal a tapestry of deliberate observation, or merely a flood of new astrophysical phenomena, the outcome will still be the same. A richer, more intricate understanding of the galaxy and humanity's delicate position within it. Ultimately, what Atlas may offer is less a message than an invitation. Look harder. Question the comforting stories we tell ourselves about the universe. Accept the possibility that humanity may no longer be only the observer, but also the observed. That realization changes us. It changes the policies we write, the instruments we build, and the way we think about protecting both our planet and our signals. The cosmos has always appeared vast and indifferent. What Atlas suggests, if it suggests anything at all, is that indifference itself may be more complicated than we imagined. Perhaps in the quiet persistence of a spectral line, in the geometry of a sunward trajectory, or in the timing of a conjunction, the galaxy has been nudging us toward a realization. Being seen is itself an event of consequence.